Hi, everyone. Hope you're enjoying the longitudinal data analysis workshop. Dr. Kozlowski and I are excited that you're all here and that you've joined us for this advanced session. If you weren't here for the first session, I want to give you kind of a quick reminder of how things will work in the practical session. Al has been presenting about a lot of the conceptual issues in applying mixed effect regression to longitudinal data analysis. And kind of talking about it from a theoretical standpoint and an abstract standpoint. In these videos, we want to walk you through how you might actually do some of these analyses using the statistical programming language R and the RStudio interface. Prior to the workshop, we emailed you with kind of some script files and these worksheets. And this gives you kind of a diverse way of working through this video and kind of working on these different problems. So I'm going to show you the handout, which I have here, and you can have R open at the same time. You can have the R Markdown document open and kind of scroll through that as you also go through the handout. But remember, if you ever want to take anything out of the R Markdown document and just run the code on its own, or have a script file where you save all of this code on its own, all you need to do is copy the text out of the R Markdown document, paste it into your own script file, and then you can click run in order to run that code and implement that code. So the first thing that we're going to do is we open up the libraries that we're going to use. If you haven't already, you would need to install these packages. Hopefully, before everything started, we sent out an email with kind of a video on how to install packages and what packages need to be installed. So if you haven't done that yet, I would encourage you to take a look at that video, but you'll need to make sure that these packages are installed in order to open them into your local library. And then once you have that done, you can go ahead and read in the data from the web in order to create the data file we're going to use. And if you're doing that in R Markdown, you can just click run to execute the current code chunk. Or again, if you wanted to actually run this in your R script, you could copy the relevant code out of the Markdown document and then paste it into an R script and then run the code there. If you want to run code in R while following along with the handout, either of those options would totally work. And we'll be running the Zoom session where you can drop in and out if you have any questions about troubleshooting the R code. If you don't want to focus on, like running R right now, and you just kind of want to see how it works, you can just watch the video and I'll be talking you through the handout, explaining the R code as we go along and providing a bit of extra, kind of background and detail that isn't necessarily in the written handout itself. So I'll mostly be sticking to the handout in this video, but again, feel free to pause the video, run R code, pause the video, write down some questions to ask us in the Zoom session. This is really flexible in terms of how you want to actually proceed with this. But if you feel at all uncomfortable with running the R code at this stage, I'd encourage you to just watch the video, try to get as much out of it as you can. And then you can always follow up with me or Al in the future about actually implementing this code and troubleshooting any issues that you might have. So again, in this practical session, when we're talking about more advanced topics, we want to turn our attention to fitting truly nonlinear models. And we're specifically going to talk about fitting a spline function and fitting a negative exponential function to the spinal cord injury data that we were working with in the previous session. So you need to open up these libraries in R. If you haven't already, you would need to install these packages. And then once you're there, you're going to need to actually download the data from the web, importing it into R to create an object called data. And then one of the things that we're going to do is we're going to create a new variable called year, where we're just rescaling our time variable from months into years, dividing it by 12. So again, if you hit any technical hurdles, feel free to follow up with us afterward. Feel free to pop into Zoom and ask us a question. But otherwise, in this handout, right, what we'll have is some supportive text that kind of lays things out. And then the actual code chunks are what's presented in the grayed areas. And this is the actual code that you would run in R to implement these different models. So the first model that we're going to talk about is a single knot spline model. In the beginning section in part one, we talked about using polynomials in order to try to capture curvilinear functions when we're looking at changes in our outcome variable over time. And one of the things that we saw in those data were that Roche scaled FIM scores did change over time for these spinal cord injury patients, and they changed non-linearly, where the rate of change was much faster early on, and then it started to flatten out as time went on. So polynomials are a useful way to capture that, but a different way of capturing that would be what's known as a spline function. And splines, you probably are not familiar with, but they're a specialized mathematical function that is defined piecewise by polynomials. And when we say piecewise, what that means is the spline takes a set of values before a discrete point, and it takes a different set of values after a discrete point. But the spline implements a polynomial function both before and after that point. So for instance, you could think about if we have a function where y is equal to 1 plus 0.5 times x, and that is the value, that is the relationship between x and y before x is equal to 5. However, if x is equal to or greater than 5, then the slope changes to 2 times x. So we have a slope that is 0.5 before a certain point, and then that slope changes to 2 after a certain point. So that would be piecewise because there is a discrete point at which the function changes, and it is polynomial because it is a linear function or a first order polynomial function. So you can have splines that take different values. They don't have to be linear. You could have cubic splines, right? And you don't have to have a single discrete point. You could have multiple points. But that point at where a function changes is called a knot. And you can have different numbers of knots, and you can have them placed like evenly across your x-axis. You can have them unequally spaced in specific locations. And like I said, you can have different orders of polynomials between your different knots. So splines can get massively complicated, and there are some additional packages that you can download and install to help you find the best fitting splines for your data. I think a good starting point is going to be dealing with a univariate linear spline that has a single knot. So that's going to be a situation where x and y have a slope before a certain point, and then they have a new slope after a certain point. And so that can be really useful, for instance, in these Roche scaled film score data, because as we can see from the Ggplot code here, right, we're going to have our Roche scaled film scores changing over time, but they change much more quickly in the beginning, and then that change starts to even out and be a lot flatter as time goes on. So what we could do is actually fit a spline to these data, where for instance, I could, let me see if I have a tool for that here. I might just have to show you with my cursor, but I could, essentially draw a line that has one slope up to a certain point, and then draw a line with a different slope after a certain point, right? And so we can fit this curvilinear function with a spline, and rather than a curve, it's going to be sort of, a kink because there's going to be a tight angle in it. And for these data, we have to decide where to put that knot. Where is the point where the rate of change changes? And visually, we could put this in a few different places, but I'm kind of inclined to place it at around 0.4 years. It seems like before 0.4, there's a pretty steep rate of change. And then after 0.4, that really starts to level off. So we can create a spline variable, which we're going to call spline 04. And this variable is going to change piecewise because we're going to pick a discrete point, specifically at 0.4 years, and where we're going to define our spline. And the way we can define that is based on the knot location, which we'll call K. So if K is 0.4, if the current year is greater than or equal to K, the spline variable is going to be equal to the year minus K. So if the current year is less than K, the value of the spline is going to be 0. And we've created a plot below to show you that in a little more detail. So let me put these two things on the screen at the same time. Here in R, we're going to create a new variable called spline 04. We're going to use the if-else function to basically evaluate if some statement is true. If that value is true, this is what it's going to do. And if that value is false, this is what it's going to do. So to create spline 04, it's first going to evaluate if in the corresponding row, is year greater than 0.04? So is year greater than K? If year is greater than K, then the value the spline variable will take is the current year minus 0.04. If, however, the current year is less than or equal to k, the value that the spline variable is going to take is 0. And that can be a little hard to think, but I think it's more clear if we plot the relationship between the spline and year, which is shown in this figure. So again, we placed our knot k at 0.04. All the values below 0.04, the spline gets a 0. All the values above 0.04, the spline gets the value of the year minus k, right? So this one was like 0.41. So we have 0.41 minus 0.4, it's, like 0.1, and so on and so forth. So now after the knot, there is a linear relationship between the spline and the year. Before the knot, there is no relationship between the spline and the year. And this is what's going to allow our model to bend at the knot and estimate one slope before that point and estimate a different slope after that point. So after we've defined our knot, we can now set up a linear mixed effects model similar to what we've done before, but we're going to include a linear effective year and our new spline variable as a fixed effect. Now, you should really test whether an inclusion of a random effect on the spline is necessary. But in the interest of time, we're going to move forward with a model that just has a fixed effect of the spline. And my reason for doing that is mostly just based on my personal experience. If you have only a single knot spline, you probably don't want a random effect of both time and the spline because those effects are going to be highly correlated, right? Like we said, after the knot, the relationship between the spline and year is linear. Before the knot, there's no relationship. So the degree of correlation is going to depend on exactly where you place the knot relative to the range of those two variables. But in general, right, it's going to create correlated variables. And if you have a random effect on year, you probably don't also need a random effect on the spline term. So as we've done before, we're going to create an object, which I'm calling mod01, which is using the linear mixed effects regression function, the LMER function, where Ross-scaled FIM scores are our outcome. And we are predicting those as a function of an intercept, the year variable, and the spline variable. And then we're going to have random effects on both the intercept and year within each subject. These will come from a data frame that we have called data. And we're going to use maximum likelihood estimation. So I set REML equal to false. If I then want to see the Anova table for these data, right, after the model has been created, I can then pass that object to the Anova function and get an output that looks like the one below, where it tells us basically the variance explained by the effective year and the F value, the variance explained by the spline and the F value. Overall, these are both statistically significant, and they explain a lot of the variance in the data. Using the summary function, we can see the actual coefficients from the fitted model in order to get this specific value for the effective year and the effect of the spline. And we can use those values to create a new data set that shows our predictions for each one. So I'm doing a little bit of fancy work here with R to generate this, but this is going to be kind of an essential step to generate your model predictions from the spline model. So I do want to pause here for a second to talk about exactly what I'm doing. So I'm going to create a new data frame called mean, and that data frame is going to consist of one variable called year, which goes in sequence from 0.0 to 0.5 in increments of 0.1. I will then create a second variable in the mean data frame called spline04. And this is going to have identical code to the spline variable we created in the data frame. So, in the data frame, I was creating spline values for each person. In this data frame, I'm just creating the overall spline values for each year. But the code looks the same, right? I'm going to use this if-else statement to say, okay, if the year is greater than the knot, then the value you take is the year minus the knot. If the year is less than or equal to the knot, then the value you take is 0. And you can see that then when I print this to the screen, this is the relationship that we get. So up until our knot, which is at 0.4, the value of the spline variable is 0. After the knot, starting at 0.5, the value of the spline increments and linearly increases along with the year variable. Then what I can do is I can pull out the actual values for the intercept, the effective time, and the effect of the spline from the summary function. So you'll get these fitted values output as estimates if you say, summary of mod 01, which we've seen in previous modules. And I'm just taking that estimated intercept, the linear effect of time, and the effect of the spline. And then I'm plugging them in to get the average estimate. What does our model estimate based on the fixed effects that the Roche scale film score should be at each time? So you can see I'm just taking the year value, plugging it in here, multiplying by 85.57. Taking the spline value, plugging it in here, multiplying by negative 69.697. And then you just solve that equation at each set of values to ultimately get the estimated Roche scaled film scores at each point in time. And now that I have those data, I can take the raw data in Ggplot, right, and actually plot the individual data for each subject. And so that's what the first part of this Ggplot code is going to do. And then at the very end, I'm actually going to add an additional geome and add lines to this plot. But I'm going to draw on the mean data. So that new data frame that we just created. And but it's going to have the same X and the same Y variables. So for the underlying plot, it's going to pull the data for the year and the Roche scaled film scores for each person. But for this final line, what it's going to do is it's going to pull the year and the Roche scaled film scores on average at each point in time. And I'm going to make that line a little bit thicker, and I'm going to make that line black so that you can more easily see, okay, here are the estimated data for each person shown as the gray lines, but overlain on top of that is our actual spline. And you can see we've put that knot at 0.4. So we have a steeper slope before the knot. And then after the knot, we have a much flatter slope. And specifically, right, if we go back to these coefficients, prior to the knot, or that is to say when the spline is 0, the slope is positive 85.57. After the knot, right, the spline, the slope is actually going to be reduced by 69.697, right? So it's actually going to get considerably flatter after that knot relative to before that knot by having the spline in that regression model. So hopefully conceptually that gives you a sense of what the spline function actually does. But an important question we've left out at this point is, how do we ultimately decide where to place that knot? We said visually looking at it, it seems like 0.4 might be a reasonable place to put the knot, but that's not actually the best way to choose. And in fact, I'd say it's a pretty poor way to choose where to put the knot in your spline. Ideally, you could place that knot at some theoretically meaningful point, such as at the end of the intervention, discharge from a hospital, or at the point where a person got a concussion. And so then you can essentially put the knot at a meaningful place and say, well, what was happening before that and what was happening after that, and how is it different? In the absence of that kind of point, we might search for the optimal knot location empirically. We can test different placements of the knot and see which one leads to the lowest Akaike's information criterion, or AIC. So empirically, we can kind of search the location of all the different knots we might want to place, and then decide, that is the best one. So that will be our unconditional time model moving forward. And now there are different packages that can help you determine the optimal knot number and location for your data. But one way you can do this with the tools that we already have is to write a for loop that will basically fit the knot in one location, or put the knot in one location, fit the model, save the AIC, move the knot to a new location, refit the model, save the AIC. And then across all of those different locations, you can actually determine where the optimal location is for placing that knot. So for those of you who are less familiar with programming, this might feel a little strange. Please bring your questions to either the Zoom session or following up with me over email afterward. But we're going to look at the splines, or we're going to create a data frame called splines. Then we're going to place the spline in different locations from basically the second month to the last month. And we're going to see where the spline makes the biggest difference and where it actually explains the most variance in our data. So some of the other things that are happening inside of this loop get a little bit technical, but conceptually, right, what I want to show you is that across those 16 different months, from the second month to the second to the last month, what we're going to do is we're going to create a spline by placing the knot at that given month and then seeing, how that affects the model. So we're going to define a new spline each time. So the first time it goes around, we're going to place this spline at month 2. We're going to fit a model, and then we're going to store the AIC, or we're going to store which month it is, and we're going to store the AIC from that model. The second time it goes around, we're going to put the spline at month 3. We're going to fit the model. Then we'll store the month and the AIC for that model. The third time it goes around, we're going to go to month 4, right? And so on and so forth. And this is going to loop all the way through until we fit splines from the second month to the second to the last month. And we will have an AIC for each of those values. So you can see it's doing this iteratively. I'm sharing the output of the for loop here, where it's just kind of printing the iteration to the screen. So it's the first loop through, second loop through, third loop through, fourth loop through, and so on, right? 6, 7, 8, 9. We're getting through this model until we get to the very end. And then what we end up with, if we actually print the final result to the screen, is that we have a series of tests, and the iterations are one off, right? So V1 is the actual month, and then this column here is the iterations of the for loop. So the first time through, it was month 2. The AIC was 556, right? The second time through, it was month 3. The AIC was 4,778, and so on and so forth. And then, we could scan through this to find, well, which month actually has the lowest AIC. The other way we could do this is use some R code to say, well, tell me which row had the smallest value for the AIC in that column. So this is a little more confusing R code, but what I'm asking it to do is show me the row from this data frame that had the smallest AIC value. And again, if you're curious about how that works, feel free to follow up with me, because the code isn't going to be immediately clear, I'm sure. The other way we could do that, the way I like a little bit better, is we could look at this graphically. And actually, let's just plot the results by looking at the AIC as a function of month, and then we'll see what we get. And you can see that our optimal knot location was actually back here at month 8. So at month 8, that gave us the lowest AIC. Admittedly, not that much lower than month 9, but low enough that it would be considered a statistical improvement above month 9. So we can move forward with placing our knot at month 8. And you can see that just how bad some other knot locations were. And this speaks to why it's an issue to potentially put your knot in a place that just visually looks right versus one that empirically looks right. For point 4, we'd be back in here, and that wouldn't be a terrible, placement, but it's definitely not the best placement because we had a lot of value added from placing our knot further along in time. And so our initial sort of qualitative choice to put the knot at year equals 0.4 doesn't hold up. And we really want to put that knot at year equals, it's going to be 0.667 because it's month 8. So that is a little confusing as well. The for loop, we iterated through months because it's a little easier to use integers to work through the for loop, but we're ultimately going to want to convert that back into years for our unconditional model. So before we had picked a spline at 0.4, but what we're seeing is statistically the best place to actually put that spline, or put the knot for that spline, is in month 8, which is to say when the year is 0.66666, so on and so forth. So we're going to then create a new spline in our data set based on what we've seen is the best fitting knot. So we're going to say if else again, evaluate if year is greater than K, right? And in this case, K is equal to 8 divided by 12. If that is true, the spline is going to take the value of the year minus K. If that is not true, the spline is going to take the value of 0. So now we'll have a spline where up until 0.66, it's going to be zeros. After 0.66, the spline will grow linearly following the value of the year. So we can plug that in with our linear effect of time and the linear effector of our spline, which we're calling spline 66. And again, we'll just have random effects for year, and we'll have an intercept and a random slope within each subject. We're pulling these data from the data frame, and we're saying REML equals false because we want to get maximum likelihood estimation. We can then use an Anova, right, for that model to get our type 3 sums of squares table. And again, you can see for each parameter, we get the variance that's being explained, the F value and the corresponding P value. These are both statistically significant, not surprisingly. But we can now see, well, what exactly is this model doing when it's telling us that there is a reliable linear effect in these data and a reliable spline in these data. So again, doing a little bit of our work here to figure out, on average, what does our model actually predict at each point in time. We can pull out the fixed effects from the model in order to get the group level intercept, the linear effect of time, and the effect of the spline. I will then just multiply the value for year by the coefficient for year. I will multiply the value for the spline by the coefficient for the spline, right? And then we can add all those terms together in order to get the average Roche scaled FIM score that is captured by the fixed effect, right? What is our model actually predicting at each point in time? And so that's what we end up with here. These are the predicted Roche scaled FIM scores at each point in time based on the spline model. Then again, using Ggplot, we're going to start by plotting the individual subject level data. So this is going to come from the data frame with year on the x-axis and Roche scaled FIM scores on the y-axis. At the end, though, I'm going to add an extra line to plot a geom line where we say, okay, now rather than the data frame, pull from the mean data frame, which is the one that we created that has all of the predicted Roche scaled FIM scores in it. But the x-axis is the same and the y-axis is the same. And what that will leave us with, right, is a new spline function where before month 8, which is to say before a year equals 0.667, the slope has one value. And then after that knot, the slope has a different value. And you can see that the placement of this knot makes a big difference compared to when we're placing it at 0.4 versus 0.66. But ultimately, we're seeing a similar story in that the rate of growth is much steeper before that knot, and then it flattens out after that knot. It's still not zero. There is still growth and change happening there, but it's a greatly reduced rate of change. So this would be a way of building an unconditional time model with a single knot spline. And if hypothetically this wound up to be our best fitting model and our best explanation, we would then carry that single knot spline forward in order to look at group level differences in the original trajectory and then the trajectory after the knot. And those would be captured, for instance, by the group by time interaction and the group by spline interaction. So next, similar to what we have done before, we're going to add in effects of AIS grade to see, are there statistically significant interactions between the linear component of the trajectory and the spline component of trajectory that differ across groups? So we'll create a new model called mod02, which uses the LMER function. And we're going to estimate Roche scaled FIM scores as a function of the intercept, the time by AIS grade, and spline by AIS grade. And as a reminder, in R, right, if we use this asterisk as an operator, it's going to give us both main effects and the interaction. If we wanted to do all the main effects and interactions manually, we'd have to use a colon operator rather than the asterisk operator. But using the asterisk is a convenient way of keeping your model a little bit smaller and your code a little bit cleaner, because I want the main effect of year, the main effect of AIS grade, and their interaction. I want the main effect of spline, the main effect of AIS grade, and their interaction, right? So by using that asterisk operator, I can get the fully factorial model without having to do a whole bunch of extra typing. Finally, then we'll have our random effects, right, where we have a random intercept and then a random slope of year within each person. Again, we'll be pulling from the data frame, and we'll say restricted maximum likelihood equals false because we want maximum likelihood estimation. We can then use the Anova function to compare our unconditional model, right, where we just said, okay, well, ignoring group, how does everyone change over time, to a model where we look at how these trajectories differ between groups. And this will show us then precisely which models are being compared. And then it will give us model fit statistics where we can make a comparison between the models to decide which one is actually better. And as we discussed in the previous practical session, we have a few different ways of doing that. One would be to conduct a walled test of the difference in the deviance between these two models. So the deviance goes down by 41.28. Now, there are 6 extra degrees of freedom for this, but even then, a chi-squared test of that change in deviance reveals that is a statistically significant reduction in the deviance, suggesting that our conditional model is better than our unconditional model. If we wanted to be more conservative, and we generally do, so we're going to use the Akaike's information criterion, right? That's going to introduce a penalty based on the number of parameters. So going from 7 to 13 parameters is a pretty big increase in complexity, but the Akaike's information criterion suggests that that increased complexity is worth it. And essentially our model's predictions get so much better, we beat that penalty for additional parameters, and our AIC actually goes down by almost 100 points. So we're doing pretty well. All right, so given then that we think the conditional model is the actual better model compared to the unconditional model, what we're going to do next is extract the actual coefficients, again, using that fixed effects function. And we're going to get the slopes and the intercepts for each group. And now this is going to be a little bit confusing here. So let me walk you through what's happening. But again, the key thing will be the concept. So if you have questions about actually implementing this in R, feel free to bring those to me in the Zoom meeting, or feel free to bring those to me afterward. But the main thing is that I want to make sure you understand the concept of what we're trying to do in order to generate these graphs. So we're going to create a mean data frame like we've done before, where we're just looking at average value of the year, ignoring subject completely. And we just want to get the model's prediction in each year. However, we're actually going to repeat our year variable 3 times, because we're going to get that year variable once for the C1 to 4 group, once for the C5 to 8 group, and once for the paraplegia group. And then we will also get values of the spline repeated in each of those groups. So essentially, we're going to have our spline variable and our year variable, and those values will repeat 3 times, because we'll have one set of values that correspond to the C1 to 4 group, one set of values that correspond to the C5 to 8 group, and one set of values that correspond to the paraplegia group. Next, we're going to ask for the fixed effects from our model, and it's going to give us the intercept, the effective year. Then it's going to give us the effect for AIS C5 to 8 and AIS paraplegia, right? And the thing to remember is that R uses treatment coding by default. So anything that doesn't have AIS grade C5 to 8 in the variable name is that value for the reference group. And the reference group is C1 to 4, because alphabetically it comes first. So R is going to use that as the reference group, and then everything else is going to get compared back to that group. So this is the intercept in the C1 to 4 group. This is the effective year in the C1 to 4 group. This is the effect of the spline in the C1 to 4 group. And all of the other values then are modifications of that formula. So what we can do down below, if we want to get the estimated Roche scaled FIM scores in each group, is we can say, all right, well, first, look through the data. And if it is the C1 to 4 group, we're going to use this formula, where we take the coefficients that correspond to the C1 to 4 group. If, however, it's the C5 to 8 group, we're going to use a different formula, where the coefficients from the C1 to 4s get modified based on the coefficients for the C5 to 8s. Because again, this is the difference in the intercept between C1 to 4 and C5 to 8. So if I want to get the intercept for the C5 to 8s, I have to add 8.8 to 6.3, and that will give me the new intercept for the C5 to 8 group. So I'm going to add all of these modifiers onto the reference group values to get a new intercept, a new effective year, and a new effect of the spline. Finally, right, it'll ask if you're in the paraplegia group, and then we'll do the same thing with the other set of modifiers, right? So to get the intercept for the paraplegia group, I have to take the intercept for the reference group and then add on the modifier for the paraplegia group. And so I'd take 8.8 plus 13.9, and that would give me the new intercept for the paraplegia group. I do the same thing for the effective time and the same thing for the spline. And what that's going to leave you with then are the unique predictions for each group at each time, and then we can plot those data. So using Ggplot again, I'm going to plot the raw data first. So I'm going to pull from the data frame where I have data for each person. I'm going to look at year on the x-axis and raw scaled FIM scores on the y-axis. And then I'm going to finish with plotting data from this mean data frame where I should get the fitted value for each group. And it's going to give me a plot that looks something like this, where you can see, all right, so in my C1 to 4s, here's how they change. In my C5 to 8s, here's how they change. And in the group of paraplegia, here's how they change. So you can see how those trajectories are getting modified in each group. And if we want to see what is actually statistically significant here, or what is different among these groups, we can start with the Anova function to get omnibus F or chi-squared tests. And then we can use the summary function to see the fitted values for the individual groups. So first, I will pass the conditional model to the Anova function. And you can see that we have, actually, let me zoom out a little bit so I can get these on the screen at the same time. You can see that we have a main effect of year. So on average across groups, there is an increase over time. There is a main effect of AIS grade, which refers then to the difference in the intercepts, right? So at the beginning, there are some differences between our groups. There is a main effect of spline, suggesting that after the knot, the slope is different than before the knot, on average across groups. And then there is also a statistically significant year by grade interaction, but no statistically significant spline by grade interaction. So we'd have to do some post hoc tests to really determine exactly where these differences come from. But in looking at that omnibus test, right, we can see that there is a year by grade interaction, suggesting the initial trajectories for our groups are all different, or at least some of the trajectories for our groups, I should say, are different. However, there is not a spline by grade interaction, suggesting that the fall off from before the knot to after the knot is pretty similar for all three of the groups, right? So we can kind of see that if we focus on C1 to 4 compared to paraplegia. The paraplegia group has a much steeper slope at the beginning before the knot than the C1 to 4s. So that is contributing to that year by group interaction. However, in both groups, there is a big fall off from the initial slope before the knot to the final slope after the knot. And that fall off is more similar. And that is why we see a non-significant spline by group interaction. Because again, the year by group effect tells us about how the groups differ in their initial trajectories. The spline by group effect tells us if the change in trajectory is approximately the same in all of those groups. So those splines can be a little hard to unpack, but hopefully this illustration helps you understand precisely what is being done in the statistical tests down here. But if you have any questions about splines or how to interpret them, please, again, do bring those into the Zoom session or follow up with Al and I on how to interpret some of these data and how to interpret some of these outputs that you might get from R. Okay. So let's take a sec there. You know, you can look back through some of the materials, rewatch some things if needed, formulate some questions. But now that we've discussed fitting single knot splines, we want to talk about fitting a negative exponential model, which is another one of the really helpful nonlinear models you're going to encounter, especially when dealing with clinical data that have a very hard ceiling effect on them. All right. So as kind of a disclaimer, negative exponential models are tough. They're pretty tricky, and it's going to take some time to really, I think, understand all the different parts of the negative exponential model if you're not familiar with working with them. But let me zoom in on this a little bit and just highlight the actual formula for a negative exponential model. So in this model, we're looking at y as a function of alpha plus beta times Euler's constant raised to delta times time. So in that model, the alpha parameter is going to define an asymptote. That's the value that a curve is going to approach but never reach. The beta parameter is going to define the total change between a person's pseudo-intercept and an asymptote. The other way to think about that, right, is if we take the difference between alpha and beta, that should capture the total change that a person shows, or sorry, if we take the difference between alpha and beta, that will show approximately what the intercept for that person was. So the difference between their intercept and their asymptote is going to be approximately beta. Finally, the delta parameter should reflect the rate of change. So the closer to zero this parameter is, the flatter that curve is going to be, or the less changing that curve is going to be over time. The farther from zero it gets, the faster that person is going to be approaching their asymptote. So for instance, you can think about a situation where, if you make time 1, so we'd be plugging in a 1 here, and 1 times delta is just going to be delta. So you can then solve for what is the value of beta e to the delta. And that constant will reflect how far the person is from their asymptote at time 1. Essentially, how much ground do they have left to make up, right? So the smaller that gets, the closer they are to the asymptote. The bigger that is, the farther they still are from the asymptote. So the value of delta is going to make a big difference here. But by thinking about, okay, well, when time equals 1, how far are they from the asymptote, or how close are they to the asymptote, kind of helps you understand what that delta parameter is doing. And it's important to dwell on the meaning of these parameters for a second, because when we're dealing with nonlinear models, and in mixed effect nonlinear mixed effect models, I should say, we have an added complication now, which is that we're going to have to provide some starting values to the algorithm in order to help it converge on the correct solution. And the short answer for why we need to do that is that these kind of models are really complicated, and the math required to search for the best combination of all parameters is really sophisticated. And you have to provide some reasonable starting point to help it narrow in on what the actual true correct values of those parameters are. Now, we'll show you a little bit about how to do that. But it's important to think about, okay, what does alpha mean? What does beta mean? And what does delta mean? Because you need to understand those variables in order to make reasonable estimates of what their starting values might be. So to understand that, let's first plot these data. And I'm not going to actually plot a nonlinear mixed effect model, but what I am going to do is I'm going to use a Lohse regression smoother inside of my stat smooth argument here. In order to plot these values. And what you can see then is here's our Roche scaled FIM scores as a function of time from admission. And you can see this kind of nice change that flattens off over time. And we get diminishing returns on the change in our Roche scaled FIM scores. So now we're going to want to pick values that would kind of go into a mixed effect model here. And to decide then, well, what is our asymptote? What is our pseudo-intercept? And what is our rate of change? We can look at these data and try to make a reasonable decision. So in looking at the data, most of the individual participants max out, well before 80 points, and the group level average certainly does. So we might pick 80 as kind of a reasonable starting point for the asymptote and say, okay, well, that seems to be close to the maximum value of what we're observing here. So let's start at 80. Similarly, the minimum value for most of the participants, is around 10, somewhere in here. And the group level minimum is, closer to like 15 if this line's about 12 and a half. So, we could pick 0, we could pick 5. I think any of those things would probably be reasonable, but I'm going to pick 10 just as a potential place for a pseudo intercept here. which means then that the difference between our estimated asymptote and our estimated intercept is going to be 10 minus 80, which is negative 70. So we're going to have then a choice of our beta parameter as negative 70, right, as I said. And that's going to be our estimate for the starting value of the beta parameter in the mixed effect regression equation. Finally, as a choice for the rate parameter, that's a little bit tricky. I'm going to pick -1 as a starting value here. And the reason for that is if you plug in -1 to at year 1, right? So we'll say, okay, assuming time is 1, what is 80 minus 70 times Euler's constant raised to the -1 power? That works out to be about 54.25, which if we look at the value at year equals 1, well, it's about 50. So -1 probably isn't too far off given our choice of the asymptote and the change parameter. So, you can play around with different values and then eyeball it on this graph. And the good news is once you kind of have an estimate of an asymptote, an estimate of an intercept, you can do a little bit of math to get an estimate of the change parameter, once you have an estimate of the asymptote, an estimate of the change parameter, you can do a little bit of math to get an estimate of the rate parameter. But even if you are off by a fair degree, as long as those starting values are in the ballpark, right, your model will hopefully converge and then tell you what the actual best values are. You have to be pretty far off for these models not to converge. But the issue is you can't just tell the computer that basically all numbers are on the table, and I need you to search from anywhere from -infinity to +infinity to try and to decide, which of these three things ultimately provides the best fitting solution, because all three of those can change at a time, and it becomes a really difficult problem for the computer to solve. So hopefully these are reasonable estimates, but we'll see if our nonlinear mixed effect model function converges when we actually run that code. So we're going to create a model called negx rand mod for a negative exponential random model. We're going to now use the NLME package. So this is different. Before we used the LMER function from the package LME4. Now we're using the NLME function from the package NLME. And the code is a little bit different. We're going to start with our dependent variable, and then we're going to have a tilde to say, okay, give me this dependent variable as a function of, and we're going to give it a variable, which I call beta or B1I, multiplied by B2 times Euler's constant, right? The exponentiation of B3 times the time variable. I'll then tell it, okay, pull this from the data set. And then I will tell it which variables are our fixed effects and which variables are our random effects. I will then tell it what the grouping factor is for those random effects. And then we're going to give it the starting values that map on to the three fixed effect values. So it's going to start searching around an asymptote of 80, a change parameter of -70, and a rate parameter of -1. So after we fit that model, we can use the summary function to look at the actual estimated values that we get. And scrolling down, we can see an output, somewhat similar to what we saw with the previous LME4 output, where it's going to give us first a description of the random effects. So we put random effects on both the asymptote and the rate parameter. We didn't actually put one on the change parameter, which I talk about a little bit in the text. But you can see that we get a standard deviation for both of these random effects and the correlation between the two. We also then get an estimate of the residuals to tell us the standard deviation of the residual errors, essentially how far off of the individual lines are our predictions on average. However, I really want to direct attention to the fixed effects right now so we can take a look at, well, how accurate are the fitted values there compared to the starting values that we supplied to the model. And what you can see is, we guessed 80 as a starting value, and it ultimately was 69, so not too far off. We also guessed -70 as the change value, and it was -62, so not too far off. We guessed -1 as the value for the rate parameter, and we ended up with -1.97. So that's considering the scale, that's ultimately farther off, but the model still was able to converge, searching the available parameter space and determining that these three values were actually the best fitting values that explain the variation in the data, giving the starting values that we provided it with. So we've successfully now fit an unconditional negative exponential model to say, well, which three values, in terms of an asymptote, a change parameter, and a rate parameter best capture the change over time in these data. The next step then, right, is to add in our conditional effects, right, and really say, well, does this change as a function of group? And this is, not surprisingly, going to get a little bit trickier, right? But conceptually, what we're trying to say is, well, all right, is the negative exponential function that defines the C1 to 4 group different from the negative exponential function that defines the C5 to 8 group, different from the negative exponential functions that defines the group with paraplegia? And the really tricky thing here then is that we're going to have a more complicated syntax in our formula, and we're going to have to provide it with some updated starting values. So based on what we can see in the figure here, and I encourage you to, maybe have this up on your screen or have a kind of split screens between the video and the handout so that you can see it. But we're going to try to look at the asymptote in each of these groups. We're going to try to look at the pseudo-intercept and therefore the change in each of these groups. And we're going to try to get some estimate of the rate parameter in each of these groups. And remember that R is going to treat the C1 to 4 group as the reference group because it is going to dummy code all of our variables. And then everything else will be the C5 to 8s compared to the C1 to 4s and the paraplegic group compared to the C1 to 4s. So this is going to be our reference group. And the other variables we'll need to provide starting values for are essentially differences, right? We'll have to provide some scores that describe the C1 to 4 group. And then we'll have to say, well, how much higher is the asymptote for the C5 to 8 group? And how much higher is the asymptote for the paraplegic group? And that is, in essence, what I am doing here. And I can highlight that value in the text. And that is what I am doing in the corresponding part of the code down here, right? So we have a bunch of different numbers here. And I can explain to you what those different numbers are if we look at the code in a bit more detail. So we're going to create a model called negx group mod 2 because it's our second negative exponential model. And this is the one that now has group in it as a factor. But we're looking at Roche scaled FIM scores as a function of our three fixed effects, right? Our asymptote parameter, our change parameter, and our rate parameter. But those fixed effects now get more complicated because it's not just B1 by itself. If we want to say, does B1 get modified by AIS grade, I have to add in that B1 itself is a function of some intercept, some default value, and the AIS grade variable. Similarly, the change parameter B2 is a function of some intercept and the AIS grade variable. B3, right, the rate parameter is a function of some intercept, some default value, and the change based on the AIS grade variable. So that is what we're going to need to supply as starting values. We're going to need to supply the value for the reference group. So I put in an asymptote of about 50 for the C1 to 4 group. We're also then going to need to define the difference in the asymptotes. So for C5 to 8, I estimated their asymptote was about 15 points higher. So let's start there. And for the paraplegic group, I estimated their asymptote was about 25 points higher than the C1 to 4 group. So let's start there. Similarly, for the change value, I said, okay, so I think it's, for about 50 to minus 35, so the intercept's about 15 for the C1 to 4 group. I thought the C5 to 8 group showed an even bigger change, and the paraplegic group showed an even bigger change than that. So negative 35 is the change parameter for the C1 to 4 group. Negative 10 and negative 15 are how much bigger that change parameter is than for the C5 to 8 group and the paraplegic group. Negative 2 then is our estimate of the rate parameter in the C1 to 4 group. And then I put in zeros for the difference in the rate parameter, because in looking at the figure, I wasn't really convinced that their rates were all that different. I thought it was more just sort of where they start and where they finished. So I just plugged in 0. You could probably plug in other small values and the model would still converge. But that's why for the rate parameter, I thought it would probably be about -10 or negative 2, excuse me, for the C1 to 4 group. And then the difference in the other groups would not be that big. So we could start at 0. With that model that successfully converges, you can then use the Anova function to obtain omnibus test results, right, to get the overall F values. And then you could use the summary function to obtain actual fitted values for the individual coefficients. So with that model converging, we can then pass it to the Anova function and get our omnibus F tests. And we'll get these F tests for the default value, right? For the intercept, and then is there a modifying effect of AIS grade on the intercept? And sorry, remember that the B1I intercept is actually our asymptote. Then we can also get this for B2, right, which is our change value. And is there a modifying effect on the change value? And then for B3, which is our rate parameter, and is there a modifying effect on the rate parameter? And indeed, there's actually a statistically significant effect of AIS grade on all of these things, right? There's an advantage of having an asymptote, right? And there's an advantage to having a change parameter in the model at all. That's not too statistically surprising, but it's really these interactions with AIS grade that we're interested in. And is there a statistically significant effect of AIS grade on the asymptote? And it looks like our groups do indeed differ in where they asymptote. Is there a statistically significant of AIS grade on then the change parameter? And it looks like there is, suggesting that as those asymptotes get higher, it's not just that the intercepts also correspondingly get higher, because then the change parameter would stay the same. But in each of our groups, it seems that as the asymptote changes, the magnitude of the change is also changing. And then finally, for our rate parameter, we see a statistically significant effect there, suggesting that I was wrong. You know, my model still converged when I picked 0 and 0, but there are actually statistically significant differences in these groups in terms of their rates. And if we want to see exactly what those differences are, we would need to come down to our output here, and then see, okay, well, exactly how, what are the values for each group? And again, anything that doesn't have AIS grade C5 to 8 in it is going to be the value, or sorry, anything that doesn't have the AIS grade name in it is going to be the value in the reference group, which is our C1 to 4s. So this would be the asymptote for the C1 to 4s. This would be the change parameter for the C1 to 4 group. And this would be the rate parameter for the C1 to 4 group. So, you know, they had an asymptote of about 45. They had a total change of about -57. And they had a rate parameter of about -4. So we were a little bit off in some of our estimates, but the model was still able to converge on what the actual best fitting values would be. And then we can see how the groups actually differ from the reference group. Right, so we can see how, okay, well, what is the asymptote for the C5 to 8s? It is 16 points higher, and that's a statistically significant difference. The asymptote for the paraplegic group was 26 points higher, and that is a statistically significant difference. Now, the change parameter for the C5 to 8s was only 1.5 points lower. Ultimately, that was not a statistically significant difference. But the change parameter for the paraplegic group was -8 points lower than -57. And that was a statistically significant difference. For the rate parameter, similarly, you know, -4 ended up being the best fitting value for the C1 to 4 group. Now, the C5 to 8 group had a lower, or I should say a more positive value, because you're adding 1.8 to -4. So that's going closer to 0. And that was a statistically significant difference. The paraplegic group also had a more positive value, because we're going to add 1.389 to -4. So we're going closer to 0. However, that was not a statistically significant difference relative to the C1 to 4 group. So, you know, the exact post hoc tests that you're going to need to do are going to change on the situation and what is or is not statistically significant in your omnibus F tests. But this is, you know, a model that converged for a fairly complicated negative exponential model, where we're estimating these nonlinear changes in trajectories over time and trying to see if the 3 different parameters that determine those trajectories are different between these three different groups. So, you know, if that feels like a lot, I think it probably should, because this is a fairly complicated research question. You know, please go back and watch some of these videos, reflect on some of the ideas that are in the handout, and come with your questions to the discussion section so that we can make sure you feel good about applying some of these ideas in your own data moving forward. And that at the very least, you know, you're kind of prepared now that you have a toe in the water to take a bigger step out into the world of fitting nonlinear mixed effect regression models. Thank you.